A summary of the mole. In this case, we're not talking about the furry creature, nor are we talking about some embedded spy, but rather we're talking about that amount. It's just a number, and it's very easy to measure it. Say we got helium. A mole of helium, check your periodic table, you'll see it has a mass of 4 grams. And those 4 grams would contain how much? Well, a mole's worth of helium, since it's a number. Avogadro's number, 6e23. As an added fact, which usually doesn't get pointed out until a later time, you can also do it volumetrically if it's a gas. Any gas, if you have a mole's worth, you got 22.4 liters as long as you're at standard temperature and pressure, 1 atmosphere and 0 degrees Celsius, which by the way is silly. At room temperature it would be close to 24.5, which is a lot more convenient. I digress. This are the two main things that people associate with the mole. How many and how much it weighs. And it's not that bad, especially if you have a periodic table. So it's good to know what the mole is. For example, a mole of carbon dioxide would have a mass of, well, let's see, CO2. Carbon is 12 grams per mole. Each oxygen is 16 grams per mole. I get 44 grams. How many molecules would it contain? I get answers from students like 1 or 44. But it's a mole's worth, therefore 6 times 10 to the 23rd. Think of it like a dozen, only way, way bigger. We should be able to measure out a mole of any substance. I need a mole of water. Can you put it in my cup, please? Yeah, H2O, 2 H's each at 1 gram per mole, oxygen at 16 grams per mole. I think I am going to mass out 18 grams. Imagine that in your glass of water. It would be not very much, right? A quarter full, something like that. Let's be able to perform chemical reactions using the mole. I need 2 moles of water, and I happen to have some hydrogen and some oxygen on my parched desert island. Can I make some water? Sure. Let's do it. I have a balanced chemical equation, 2 to 1 to 2. I should mix, well, 2 moles with 1 mole, but 2 moles weighs 4 grams. Since each hydrogen is 1 gram and we have 2 H2s, so 2 times 2 is 4. I have 1 O2 at 16 grams per mole, but it's O2, therefore I mix 32 grams and I'll make 36 grams of water. We should also be able to figure out how many molecules are involved. That reaction there, it required 2 moles of hydrogen, so that's 2 times Avogadro's number. 2 times 6 times 10 to the 23rd is 12 times 10 to the 23rd, which is 1.2 times 10 to the 24th. Typo, that's a typo right there. Do you see it? Make sure you recognize that. That should be to the 24th. That is 2 moles. It will require only 1 mole of oxygen, even though I see an O2. That's molecular oxygen. They're paired up into 1 molecule for every 2 oxygens. So we need 6 times 10 to the 23rd, 1 mole's worth of oxygen. That's 1 mole. And it will make 2 moles, or 1.2 times 10 to the 24th. Again, there's the typo. Please make sure that's 10 to the 24th. We're doubling Avogadro's number, and that is 2 moles. Let's be able to do some percent composition. That shows up a lot. Take any substance. You want to know what percent of each element is present within it. Let's do ammonia. Can you see that ammonia is 14/17 nitrogen? Here's how I did that. Nitrogen is 14 grams per mole. Check a periodic table. You'll see that it's true. Hydrogen is 3 grams per mole. And once again, more precise numbers are better, but this gets the point across. 14 of the 17 grams in a mole of ammonia came from nitrogen. Therefore, it's 82% nitrogen, 17% hydrogen. This level of precision suggests that somebody did the 14.01, perhaps is what it is for nitrogen, etc. I think it's like 1.008 for hydrogen. Okay, let's go ahead and turn that into an empirical formula for some substance. Well, let's see. It's 87.42% nitrogen, and the rest is hydrogen. Convert that to moles, where 14 grams is a mole, and then convert that into moles of hydrogen, where 1 gram is a mole, and you get a ratio of Look at that, 6.28 to 12.56. I think we're talking NH2. And so that would be its formula. If they told you that instead of being 16 grams per mole, if it's 32 grams per mole, it must be N2H4. And there it is, 32 grams per mole. So NH2 is the empirical formula. N2H4, which is hydrazine or rocket fuel, is your molecular formula. We should also be able to do standard conversions, 1-step, 2-step, and 3 steps. So if we were burning 1 mole of water, there's your balanced chemical equation right over here if you need to refer to it. The combustion of 1 mole of hydrogen will make 1 mole of water because 2 to 2 is the same as 1 to 1. If we have 4 moles of hydrogen there, we will make, looks to me like 4 moles of water. Once again, a 1-to-1 ratio. But how many grams is that? Well, 18 grams is a mole, so we're talking 72 grams of water. Let's burn 4 grams of hydrogen and find out how many grams of water it makes. Well, I know that's 2 moles, so I'm not going to bother with the 3-step conversion. I know that's 2 moles since 2 grams is a mole, and I want to know how many grams of water. Well, it's still a 1-to-1 ratio, right? 2 makes 2, so I'm going to make from 2 moles of water at 18 grams per mole. I'm going to make 36 grams of water. Now, we were able to do those nice and fast because it kind of followed us down the garden path. Normally, you'll have to do a 1-step conversion for this, a 2-step conversion for that, and a 3-step conversion for that. Refer to the screencast if that seems a little sketchy. Okay, we should also be able to do limiting reactants, and after you read all this stuff, you got 1 gram of hydrogen and 1 gram of oxygen. Perhaps we can do 2 3-steppers, see how far each one takes us. The lower number is the one you circle because that's the one you've run out of first and the reaction halts. Or you could say to yourself, I don't want to do that. I want to just look at it and consider the molar ratios. 4 grams of hydrogen requires 32 grams of oxygen, but I only have equal gram amounts, 1 to 1. I don't have anywhere near enough oxygen if 4 requires 32. Oxygen is my limiting reactant, and I summarized it here. You may also note that you can do this by inspection. Oxygen's the limiting reactant since 4 grams requires a whopping 32 grams of oxygen, and we only have 4. So I would probably skip this top calculation if I wanted to do it fast. But to be a good boy, I'm going to do the whole thing out. 2 grams is a mole. Every mole of hydrogen will produce the same number of moles of water, for which each mole weighs 18 grams. We got enough hydrogen to make 9 grams of water, but we don't have enough oxygen. 32 grams is a mole. Every time I react a mole of oxygen, it will make 2 moles of water with the same mass, 18 grams, and the reaction stops after 1 1/8 grams of water. That's the one you circle. Oxygen's your limiting reactant. Finally, we should also be able to calculate the yield of a reaction, where the yield is just how you did compared to how you could have done. It's not unlike a score on a test. For the above chemical reaction, somebody only isolated half a gram of water. Perhaps they spilled some. The yield is 0.5 for every 1.125 times 100. Right? Think of it as a score on a test. If you got 1.08 grams, ooh, you're in the A range. But we're just going to do actual over theoretical times 100. Actual was 0.5. The real, that should be a 0.5. I see 0.5 here. So this should be slightly lower. The yield will be closer to 50%, but you get the idea. Okay, this is a summary of them all. The only subject that we didn't cover that was covered in the screencast, by the way, was combustion analysis. So have a look at that screencast if you'd like to review that as well.